In this video, we are going to talk about evaluating limits graphically. Okay, so we're going to use the graph of a function to evaluate some limits. So let's start right away with an example. Okay, so this is the graph of a function y equals f of x. So this graph has a lot in it, a lot of points drawn, some holes. It's got some vertical asymptotes and some horizontal asymptotes. So let's evaluate the following. So let's begin with f of a -3. So f of -3 is asking when we plug -3 into our function. So -3 on the x-axis, -1, -2, -3. Here's -3. Where's the y value? And the y value corresponds to this point up here, which is 5. So f of -3, that would be 5. Okay, what about part B now? Part B is asking, well, what's the limit as x approaches -3 of f of x? So let's recall from our definition of a limit that when we write x approaches -3, that means that x gets close to -3, but, and here's the important part, it's not equal to 3. It's not equal to it. Okay, so that is super critical there. The fact that we know that x is getting close to -3, but it's not allowed to be equal to -3. So when we see this limit, this whole thing, what it's asking us is, as x approaches -3, from either side, whether we're larger than -3 or smaller than -3, so either side, what do the y values, because the y values is what f of x is, what do the y values approach? So looking at my graph, so here's where -3 is. So as we get close to -3 from the left-hand side, so that's this part of the graph, the y values seem to converge on whatever the y value of the whole is. And even from the other side, as you get really, really close to where -3 is, the y values get really, really close to, it looks like this is 1. The coordinates of the whole are -3, 1. And that's our limit right here. Our limit equals 1. So the fact that there's a hole there doesn't mean the limit doesn't exist or something like that, because we don't care what's happening exactly at -3. We just care about what's happening close to it. All right, so now let's do another one. So that was part B. Let's do C. Let's do the limit as x approaches 1 now. Okay, so as x approaches 1, what would this limit be? So here is where 1 is. So this limit does not exist. So let's think about the reason. And I actually want you at this point to pause the video for about 1 minute and see if you can identify why this limit does not exist. What the reason is, the precise reason. 4, 3, 2, 1, pause the video. Pause the video for about a minute and see if you can determine what that reason is. All right, so hopefully you've done that. Hopefully you've paused the video for about a minute to think about this. But the reason is that as x approaches 1 in this graph, f of x, in other words, the y values, f of x approaches 2 values. Because from the left-hand side of 1, here's 1, from the left-hand side, it seems like the y values get super close to 5. But from the other side of 1, it seems like the y values approach 2, because that's the y value of the whole. Oh, sorry. From the left, they don't approach 5, they approach 4. Sorry, I got confused looking at the 5. So from the left, the y values seem to approach 4. From the right of 1, the y values seem to get close to the y value of the whole, which is 2. So f of x is approaching 2 different numbers here, not 1. It seems to be approaching 4 and 2. But a limit, for it to exist, needs to just be approaching 1 finite number. Okay, so next I want to introduce this notion of a one-sided limit. Okay, so I want to introduce what it is, define it, and then let's do some examples. So if I write the limit and then underneath that x approaches a with a plus sign, kind of where the exponent would be, of f of x, that means the limit of f of x as x approaches a from the right solely. So that means x needs to be larger than a if we're to approach a from the right-hand side. We can also talk about the left-handed limit. So the notation is the limit as x approaches a with a minus sign written in the exponent of a, f of x here. And that's the limit of f of x as x approaches a from the left. And if x is approaching a from the left, that means that x better be smaller than a. Okay, so these are some definitions, but now let's do some examples with these. Okay, so in D, I want to know what's the limit as x approaches 1 from the right, because that's what the plus sign means. It means from the right of my function. Okay, so in terms of, let's zoom out so I can look at the graph. Okay, so I really want to zoom out so I can still look at the problem, but also look at the graph. This is asking, as x gets close to 1 from the right, what are the y values approach? Actually, you know what, I'm going to just go up to the graph and zoom in on the graph so I can talk about this a little bit more easily. Okay, so as x gets close to 1 from the right-hand side, that means I'm going along the graph this way. So I'm tracing it out in blue, getting really close to the hole. So the y values are getting super close to the y value of the hole, which is 2. And that's my limit. That's my limit from the right. So this is 2. The next part of the question, E, is going to ask, well, what's the limit as x approaches 1 from the left? So if I'm going to approach 1 from the left, and I go up to the graph, now we are going to be tracing. I'm going to be tracing this part of the graph, because this is the part of the graph as x gets close to 1 from the left-hand side. But the y values there are getting close to this point, and the y value of that point is 4. So that is my limit from the left. Okay. All right, so we've done a couple of examples of these one-sided limits. So next I want to state a really important fact about one-sided limits and their connection to a limit existing or not. So it turns out that a limit as x approaches a, so this is a two-sided limit here, so because there's no plus or minus written. So this whole thing is like a two-sided, I'll call it sometimes, a two-sided limit. Or sometimes I'll call that like an overall limit or a regular limit. A limit as x approaches a of f of x, a two-sided one, exists if and only if the limit as x approaches a from the left, because that's what the minus sign means, of f of x, equals the limit of f of x as x approaches a from the right, because that's what the plus sign means. And moreover, both of these one-sided limits need to be finite. So it's not enough for both of them to just be like infinity. That would fall into D and E category. They need to be equal, and both of them need to be finite. All right, so let's do some more examples. All right, so in the next example, part F, let's do the limit as x approaches 3 from the left. So let's look at the graph. Let's zoom it out a little bit, and let's look at the graph. So as x approaches 3, so 3 is actually where this vertical asymptote happens. So the vertical asymptote occurs at 3. And as x approaches 3 from the left, that is this part of the graph. I'm going down, coloring this in orange. And that seems to be negative infinity. So that is what the limit is. It is negative infinity. So remember that, so I want to write a comment here. Although infinity and negative infinity, they fall into the D and E category technically. In fact, let me really make D and E stand out. Let's put that in red. They fall into the D and E category. So if a limit is infinity or negative infinity, it does not exist. Although that's the case, if a limit is infinity or if it's negative infinity, we must specify that. So it wouldn't have been wrong in f to say that it does not exist, because it technically does not exist, but it's just not specific enough. Because the limit as x was approaching 3 was getting infinitely negative, we need to specify and say that. And writing negative infinity is how we get specific about that. Okay, so let's do part G. What's the limit as x approaches 3 from the right-hand side? So as we approach 3 from the right-hand side, now that's this part of the graph. That's getting close to the asymptote this way. So the y values there are getting infinitely large. So this limit is positive infinity. Positive infinity for that one. Okay, so this comment about what if we have infinity or negative infinity falling into the D and E category, we need to specify that. That applies for both of these. Both of these technically are D and E, but because we can be more specific, we need to be more specific. Okay, so finally let's do H now. What's the limit of f of x as x approaches 3? So this is a two-sided limit. So looking at these two limits, they are different. One's negative infinity, one is positive infinity. So I just get to say D and E right away. This is D and E since the one-sided limits are different. Since the one-sided limits are different. So actually, even if the one-sided limits had been the same, actually, we're actually going to see that in part I. So I'll save that discussion for part I. Okay. So I'm glad I asked part I for that specific reason. So I is asking, well, what's the limit as x approaches 5? Well, as x approaches 5, this is a two-sided limit. So I need to think about what happens from both sides and ask myself, are they the same? So from the left, as we approach 5, the graph is going down towards this vertical asymptote. And as we approach 5 from the right, the graph is also going down towards the vertical asymptote, but from this side. So from both sides, the graph is getting infinitely negative. So it's sort of going to negative infinity, which falls into the D and E category. But we've mentioned that if we can be more specific, like if it's negative infinity, or if it's positive infinity solely, we need to specify that. And in this case, it is negative infinity. So I should specify that. Okay. So this specifying thing applied to these two, and it also applied to this one, even though all three of them technically were D and E. All right, so next I want to talk about infinite limits. So part J of this example is asking, what is the limit as x approaches infinity of, what is the limit of f of x as x approaches infinity? Okay, so when we write x approaches infinity like this, this means as x gets infinitely large. So what's happening to f of x, to the y values, as x gets infinitely large? Well, as x gets infinitely large, we're looking way, way, way over here on the right-hand side of the graph. We're looking at this part of the graph. As x gets really, really big. As that happens, the y values seem to approach this horizontal asymptote. And the horizontal asymptote is going through the number 3. In fact, the equation of that line is y equals 3. So that is what we say this limit is. The y value is getting really, really close to 3. Okay. So what about part K? What is the limit as x approaches negative infinity? So that is looking at the other tail end of the graph. So as x gets really, really negative, that is looking at this tail end of the graph. And on that tail end of the graph, the y values also get infinitely negative. So we need to say this is negative infinity. Okay. All right, so I want to do just one more example here in this video, and that is part L. What is the limit as x approaches -4 of f of x? So as x gets close to -4, so -4 is here on the graph. And at -4, there's nothing really weird that happens. There's no holes, no asymptotes or anything like that happening. So we could just sort of read this off from the graph. As the x values get really close to -4 from either side, either from this side or that side, the y values approach what the y value is at this point. And that is 0. That's what the y value is at that point. It crosses the x-axis there. So in terms of our goals, we've now discussed how we can evaluate limits graphically. Like I mentioned in our overview video, we'll talk about another way to evaluate limits more precisely, and that is algebraically, but that will be in section 3.3. In the next video, we will actually be beginning section 3.2, and over the course of these last few videos, we've actually done learning goal 2 as well. We've talked about how we can recognize when a limit exists and when it doesn't. We talked about that in this video in terms of looking at the one-sided limits. And we also talked about it in the last video where we drew a few pictures of what scenarios of a limit not existing would look like.